I had mentioned previously that it would take some time before I discovered why it was that this concept of the quantity of motion that we call the momentum, the mass times the velocity measured in Newton seconds, it would take some time before I realized why that was a useful idea, why it was a good idea. And the answer to that question lives right here in the impulse momentum theorem, where the change in momentum delta P is equal to the net force multiplied by the time. Well, what if the net force is equal to zero? If the net force is equal to zero, then the entire right-hand side of the impulse momentum theorem would be equal to zero, and it would mean that the change in momentum is equal to zero. If the momentum is a quantity that does not change, then the language that we use in our physics is that that quantity, the momentum, is conserved. We call this the law of conservation of momentum. In the absence of any external forces acting on the system, the momentum of a system remains unchanged. Here's this fun cartoon example here with a cannon firing a cannonball. Hopefully we all know from experience that when you do that, the cannonball is shot out here to the right, and the cannon moves to the left. The thing is, before you fire the cannonball, before you light the fuse and the cannon goes off, the total momentum of the thing is zero. Of course the cannonball has a mass, and the cannon has a mass, but they have no velocity at all. They're just there chilling. And then boom, the cannon goes off, and all of a sudden, there's velocity, there's momentum, and there's definitely force, because the cannon exerts a force on the cannonball to accelerate it. That's how Newton's second law works. But Newton's third law tells me that when the cannon exerts a force on the cannonball must exert an equal and opposite force back on the cannon. So not shown in the diagram, but there are two forces. A force to the right that accelerates the cannonball, and a force to the left that accelerates the cannon. But I don't have to worry about those forces in my impulse momentum theorem, because those forces, being equal in magnitude and opposite in direction, add up to zero. Any forces internal to a system, forces that the system exerts on itself, they're all action-reaction, they all add to zero, and so they never even show up here in the first place. All I have to worry about is forces from the outside. Now there may be a bit of friction between the wheel of the cannon and this bit off the back of the cannon that rubs against the ground, and that would be an external force that would mess things up. But if I can make the system work in such a way that there aren't outside influences messing with it, then the change in the momentum of the system is always going to be equal to zero, provided there's no external forces. The same is true of the work-energy theorem. As long as there's no forces doing work, then the energy is conserved. Well, as long as there's no forces from the outside messing things up, then the momentum is a conserved quantity. Let me get specific about it. Imagine that I have two objects here. Object A, which is moving with a velocity VA, and object B that's moving with a velocity VB. I want to be clear. Their masses might not be equal. That's fine with me. And the velocities might not be equal. That also is fine with me. I don't mind any of that. I do need them to be traveling toward one another, because what I want to happen is to have them collide. Here I've shown them an instant later when they're actually in physical contact, and I know that what happens is that A will exert a force on B that I call FAB, and that B will exert a force on A that I call FBA. It's not any kind of universal naming convention. I'm just saying the force that B exerts on A and the force that A exerts on B. Just like the cannon and the cannonball. I just need to write my physical laws in a way that they're not in a specific context. So A and B interact with each other, and those forces are guaranteed by Newton's third law to be action-reaction forces, which means their magnitudes are equal. It also means their nature is equal, but it doesn't help me with my momentum. But their magnitudes are equal, and their directions are opposite, so they're guaranteed to add to zero. So that when these two things interact, A and B, the momentum is conserved. Why does that statement make me happy? It's because I have no idea what those forces are. You remember, in order to understand the friction force, I hooked a spring scale to a box and pulled it along. And I measured the friction force in the context of what the spring scale measured, because I said I didn't have a frictometer, a device that I could stick in there and directly measure the force. I can't get in there between A and B and measure how much force there is. It can't be done. The thing is, I don't know the forces. I don't know the forces at all, and this is the simplest thing that I can imagine. The interaction between A and B is so simple because there are only two forces. This is fantastically more complicated. Two automobiles smashing headlong into each other. How many forces do you imagine? Hundreds? Thousands? Tens of thousands of force vectors? Bits of metal and plastic and glass shattering, liquids shooting out? All kinds of nonsense going in here so that it's impossible for me to work out what the forces are. I simply can't know it. And if I can't know what the forces are, if I can't know the forces, how am I going to F equals ma? Can't be done. If I can't know the forces, I can't F equals ma, and I can't solve this problem, and my physics stops. Luckily, despite the fact that this situation is super complicated, every single one of the myriad of forces in this interaction is an action-reaction pair. They all add up to zero. It doesn't matter how complicated this collision is between these cars. It doesn't matter how complicated. The momentum is conserved. So it doesn't matter if the forces are complicated, and it doesn't even matter if I don't understand the nature of the forces. Maybe some of them are spring forces, maybe some of them are friction forces, some of them are normal forces, or maybe, it's not really the case, maybe there's a force in there that nobody's ever discovered. It doesn't matter because they all add up to zero. The situation is crazy. Everything changes except the momentum, because the momentum is a conserved quantity. Let me do what I do and turn this idea into math or a mathematical expression. It's called the law of conservation of momentum. Well, I already understand one conserved quantity, that is the energy. And the way I work the conservation of energy is I figure out how much energy I have to start, and then I set that equal to how much energy that I finish with. And in the law of conservation of energy, I have to be careful. Maybe there's some work done that increases or decreases the energy. But if there's no work done, then how much energy I have at the start is how much energy that I have to finish. So here, I've written that as an equation. What I mean by how much energy I have to start is the momentum of A plus the momentum of B. Both objects can have momentum. In the case of the cars are traveling toward each other. They definitely have momentum before they collide. One of them has momentum that I can calculate. The other has momentum that I can calculate. Be very careful. I have harpoons on these momenta here, A and B, because they're vectors. In my situation of the cars colliding, if the car going to the right is chosen in such a way that it has positive momentum, then the car that's going to the left has negative momentum. You can't just add up the Newton seconds. When you calculate this left-hand side, when you calculate that, you have to respect the fact that the momentum could be positive or negative, and that's in solving problems, in order to get answers, to score points, that's where we're going to get in trouble. If you refuse to respect the fact that momentum's a vector and can be positive or negative, this equation's going to get you in some trouble. That initial momentum is not going to change because the momentum is a conserved quantity. So the momentum after should be equal to that. To calculate the momentum after, I simply calculate the momenta and add them together as vectors. Here's a curious thing. These little tick marks on PA and PB are called primes. And you have a right as a student of physics to be frustrated by that. Because up until this point, I have said the initial velocity is v naught and the final velocity is v. I even said, the last time I talked about the impulse momentum theorem and solved some problems, I said that the final momentum is p and the initial momentum is p naught. And now all of a sudden I'm changing the notation on you, and you have the right to be grumpy about that. It is nothing more than physics tradition. I'll just for a second say why this annoying thing is happening. With our modern computers, when we typeset things, we type out an essay, all the fonts and all the punctuation, they get placed real nice. You start doing sciencey things and you have to stick equations in, your mind should go to, well, there's an equation editor, and I just use the equation editor and plunk an equation into my file. Well, that's when you have computers. Back in the day, there was no computer publishing. So in order to write about momenta, physicists had to use different notation because they couldn't have double subscripts. So you couldn't have the momentum sub A sub naught. It was double subscript. You couldn't publish that. So they used primes to signify the final momentum, and we never got over it. We just never stopped doing that. So it's notation for a reason that is now out of date. So I apologize, but you're just going to have to in this case. And since we have a 12 sheet later on you'll be working on, you could make a note of it there. Unprimed is initial, and primed is final. It's just going to take you a bit to get that. Now, that's the conservation of momentum. How much momentum you have before is equal to how much momentum you have after. But it's more useful if I unpack it. How do I calculate the momentum of A? It's the mass of A times the velocity of A. How do I calculate the momentum of B? The mass of B times the velocity of B. It's just that simple. They're vectors. Be careful. They could be positive or negative. And the final momentum is calculated as the mass of A times the final velocity of A, here indicated with a prime, plus the mass of B times the velocity of B after a collision. And that's the equation that I'll be writing out. Just like I write the conservation of momentum equation out, get all of my values in the right location, because the equation expresses the nature of the conservation of momentum, and I can make predictions about what a physical system is going to do. By way of example, consider this. Here's Twig, and he's running along at 5 meters per second, which is pretty gosh darn fast. That's good. Sprinting along at 5 meters per second, he has a mass of 40 kilograms. So I know how much momentum he has right off the bat, because his momentum is his mass times his velocity is 200 newton seconds of momentum. The boy has momentum. There's a skateboard sitting over here. Now, a skateboard has a pretty low mass, but in order to make the calculation work out interesting, I made the skateboard pretty massive. It happens to be a 10 kilogram skateboard, which is, wow, that's a heavy skateboard. He's going to run and jump on to the skateboard. And I want to know, how fast will he be going after he jumps onto the skateboard? And a non-physics person might say, well, he's going 5 meters per second. He'll just keep going at 5 meters per second. No, that's not what happens. And there's a couple of reasons or a couple of ways to think about why. When he jumps onto the skateboard, there's a friction force between him and the skateboard in the opposite direction he's moving. That friction force will slow him down. I expect the velocity to be less. That's one way of thinking of it. Another way of thinking of it is he's running along with a certain momentum, but then he jumps onto the skateboard, and now he and the skateboard move together, and the mass is increased. So I expect him to be moving slower. There are lots of ways to rationalize your way through, appropriate, physical ways, that his velocity might be less after he jumps onto the skateboard, but the momentum is conserved. So I'll use the law of conservation of momentum. Initially, the momentum of Twig running along is simply his mass times his velocity, and I've chosen him to be A in this calculation. Mass of A, velocity of A. 40 times 5 is 200 newton seconds. Notice I deliberately put a plus in front of it. I mentioned previously, but that as a habit, we don't put plus signs in front of positive numbers. But the fact that I'm saying that his momentum is 200 newtons per second means that I have chosen that in the direction he's moving, that's the positive direction. Nobody was surprised by that because we usually choose to the right to be positive, but that's the positive direction. So he's got 200 newton seconds of momentum. Before he jumps on the skateboard is not moving. And so the momentum of the skateboard is the mass of the skateboard times its velocity, which is 10 times 0 is 0. The skateboard has no momentum. And then he jumps on. And I want to find what is his velocity afterwards. Well, here is the law of conservation of momentum. The momentum is the momentum. However much momentum he had to start, That's how much momentum he has to have in the end. And so his 200 Newton seconds of momentum becomes mv of twig on a skateboard. Well, twig on a skateboard is the 40 kilograms he had initially plus the 10. So it's actually 50 kilograms of mass, which is why the speed is lower. But let's calculate. Writing out the conservation of momentum, the 200 Newton seconds of momentum he has initially has to be equal to 50 times whatever the speed is. So simply dividing by 50, v is 200 Newton seconds divided by 50, and his speed is lower. He slows down. Well, not just he. He slows down, the skateboard speeds up, and their final mutual velocity, moving together as one thing, is 4 meters per second, slower than his initial running velocity. In terms of forces, I can explain it. Twig's going at 5. He's running along at 5 meters per second. And then he jumps on the skateboard. The skateboard pushes back on him, and that slows him down to 4 meters per second. The skateboard is sitting there chilling. Twig comes along, jumps onto it, exerts a force on the skateboard that makes it speed up to 4 meters per second, and now they're both moving at 4 meters per second. That's all Newton's second law reasoning. A force causes acceleration, which changes velocity. Here's the problem. How much friction is there between Twig and the skateboard? Nobody knows. Nobody knows. And it's very complicated. It's very complicated. I would even go so far as to say it's possible to approximate it, but it's impossible to calculate it. I can't know what the forces are. Luckily, I have the conservation of momentum, so I can predict the velocity after this complicated interaction without knowing anything about the forces involved in the interaction. And that is the value of the law of conservation of momentum.